Hey guys, welcome back. This is now going to be on question 4 in the 2026 AP Chemistry FRQ exam. Let's go. White phosphorus P4 can decompose into P2 at elevated temperatures. A balanced chemical equation, Kp expression, and Lewis diagram for the chemical species involved in the reaction are given. Part A. The average bond length in P4 molecule is 221 picometers, whereas the average bond length in P2 molecule is 189 picometers. Explain why the average bond length in P4 is greater than the average bond length in the P2. All right, let's go solve this. This is question 4A. All right, 4A. All right, so what do we know? The easiest way to look at it is what? Look, right? These are all single bonds, and in P2 it's triple bonds, right? You would say uh what is that asking you? Explain why the P2. Okay, so P4, right? All of bonds in P4 are single bonds, right? Or all sigma bonds. We can use the symbols the reader should recognize. All sigma bonds. Whereas um, in P2, um, one, whereas in P2, the the triple bond is comprised of, what do you think? Triple bond. How many sigmas, how many p's? You should know that, right? One sigma and two pi bonds, right? And pi bonds are shorter, right? Why? Because they hail from side to side orbitals, right? They have to reach over. Whereas um, the whereas a sigma bond is longer because they are made of end-to-end orbitals. Now, could you get away with by just saying that a triple bond is shorter than a single bond? I maybe, but it's kind of a weak answer. In a college level class, I wouldn't give you credit for that. All right, let's go to B. Um, a sample of P4 is placed in a sealed rigid container and heated to 600 kelvins, at which point initial pressure of P4 is 0.470 atmospheres. Some of the P4 then decomposes into P2 as the system reaches equilibrium. At equilibrium, partial pressure of P2 is determined to be 0.630. Part B, calculate the value of the equilibrium constant Kp for the reaction. Show the work that leads to your answer. All right, so let's go 4B. All right, so how should we solve for 4B? This is really stupid, isn't it? Right? If the right sample of P4 is placed in it. All right, so let's just write it out, right? If you got a P4, right? Going back and forth to P2, it's a sample of P4, and at which point initial pressure is 0.470. Right? Some of the P4 decomposes into P2 as the reaches at equilibrium. Partial pressure of P2 is determined So change and equilibrium. At equilibrium, P2 is going to be 0.630, right? And they want the what? This can't be this simple, right? All right, so what do we know? Well, we have that, and do I have the yep, so you need that. Okay, so now it's a balanced equation. All right, so now what? We know that it started with none, right? And how do we get there? We got there by doing this, right? And what do we know? For every one of every mole of P2 that was created, half as much was used, right? So therefore, in order to create 0.630, half of that was used up, right? So that's 315. Am I right? So half of 36, that should be right. Yes, yes. So now what is the equilibrium constant? Not the equilibrium constant. It's going to be 0.470 minus 0.315. That gives us a equilibrium pressure of the P4 as 0.155. All right. So now what? It says for 4B, what calculate the value of the equilibrium constant. So then with the Kp. So let's go. Kp is going to be equal to pressure of P2, right? Ah, it's Kp. Come on. Hello. It's going to be pressure of the P2 squared, right? Remember the coefficient over partial pressure of P4. Okay. Love how they use phosphorus so that their multiple P's are trying to confuse you with like, with this. They're not actually making this hard because of chemistry. They're just trying to make it confusing, right? All right, so we got that. So what do? We got to plug in the values, right? So what do we got? We got P2 is going to be 0.630, and that is squared all over. P4 is 0.155. And what does that come out to? 0.63 squared divided by 0.155. That gives me a Kp value of, with three sig figs, 2.56, right? Kp is equal to 2.56. Right, then there's my work. Let's go. That's done. That was done. Part C, the reaction is thermodynamically favorable under the standard conditions only at temperatures above 1500 kelvins. A student claims that the reaction must be endothermic because it's favorable only at high temperatures. Do you agree or disagree? Just so using entropy and enthalpy and Gibbs free energy. All right, so this is Gibbs free energy. Let's go. For C, all right, so how do we go about explaining this? Well, we need the equation, right? What's the equation? The equation is Gibbs free energy is delta G is, and you have to memorize this, I think, right? I don't think it's on the reference table, right? It's H TOS. That's how I remember it. H minus TOS. All right. So in order to figure this out, right? I don't know if you know, but you have to know what conditions are what. Negative delta G is spontaneous, right? So what do we know? We have a situation where the values in here, right? If you have a negative delta H and positive delta S, right? What do you end up with? You end up with a delta G value that's always going to be spontaneous. So in this case, it's going to be always. All right, what else? There are two other cases, and then you have the other extreme case where if you flip it the other way, where you have an endothermic condition, right, in terms of enthalpy, and then your entropy goes negative, then what do you end up with? No matter what values you put in, it's always going to be positive. So this will be never spontaneous, right? And then in between, you have the condition where it's going to be both negative or both positive, right? Let's take a look. In a negative condition, this delta H being negative right here is going to help delta G. I'm sorry, delta H being negative right here is going to help delta G being negative. However, the negative T delta S, where the entropy is going to be negative, that's going to give you a positive value. So the only way to make sure this is negative is if this entire thing is small. So therefore, this is at low temperature. Okay. And over here is the other way. Delta H is going to be positive. That's not going to help the delta G be negative. It's going to, go against it. So the only way this is going to be negative is if this entire expression of negative T delta S is going to be very, very negative value. How do you get to that? A negative T times positive delta S is going to give you a negative value. So this is going to be at high temperatures where you're going to get usually a delta G of negative. And this, I think, is the condition we're talking about right now. All right, so what do we know? Um, if delta H is positive and delta S is negative, only at high temperature will delta G be negative. All right, so let's go. Reaction is thermodynamically stable, blah, blah, blah. Student claims that the reaction must be endothermic because it is favorable only at high temperatures. All right, so endothermic means delta H is positive, right? Therefore, student makes sense. So, do you agree? I write, I agree, right? Um, at if uh delta H is positive, endothermic. Um, delta G will be negative at high temperatures. Okay, that's 4C. Let's keep going. 4C is done. Ooh, that's it. This is question 4. That was easy. All right, so I'm going to end here. I'll see you on the next one.